Okay, let's take a look at a couple more examples of a geometric series. Remember, a geometric series is a series, an infinite series, where you're multiplying the previous number by the same number every single time. Okay, a repeating decimal is always the sum of a geometric series. So let's look at one example here. So let's say I ask you to rewrite the repeating decimal 0.08 repeating as a fraction, basically. So let's think about what 0.08 repeating is if we wrote it out. So this is the same as really 0.08. This is really 0.08, 08, 08, etc. So then to get the next 08, we would have to add 0.0008. That would create these first four numbers. And to get the next one, we get 0.0008, etc. Right? Okay. Now, let's write this as a fraction, and it may be easier to see. So this is 8 over 100, right? The first number after the decimal is the tenths, and the next one is 100. So the next number is 8 over 10,000, right? We're just adding 2 zeros every single time, and this pattern continues. So notice here, what are you doing every single time? Your R value is 1 over 100. You're just multiplying by 1 over 100 every time. So this is a geometric series that converges. So to find the sum of this geometric series, it would be A, which is the first term, which is 8 over 100 over 1 minus R. So let's clean this up. If you do 8 over 100, this is 99 over 100. This drops out, so this is 8 over 99. So if you type in 8 divided by 99 in your calculator, you will notice that you get 0.08 repeating. So this is equal to this number. So let's try this one, same idea. So let's try 0.23 repeating. So this is really 0.23 repeating is the same as 0.23. And then you would have to do 0.02023. And then 2 more zeros. The pattern continues. So again, if I rewrite it as a fraction, same thing happens. And again, your R in this case is also 1 over 100. So I know it converges. So the sum of this series is going to be A, the first term, all over 1 minus R. And this is 23 over 99. And you can do this for any repeating decimal. Like 0.3 repeating is exactly 1/3. So hopefully we know that, but that's another repeating decimal you can do that with. Okay. Let's look at one other example, two last ones actually. So this one says a person with an ear infection is told to take an antibiotic tablet, ampicillin, regularly for several days for every 6 hours. Each tablet is 250 milligrams, and after 6 hours, 4% of the antibiotic remains in the body. Since the drug is being excreted by the body in between doses, how can we calculate the quantity of the drug remaining in the body at any particular time? So let's say when the person first takes the medicine, the amount of drug in the antibiotic in the body is going to be exactly 250 milligrams. Okay. Now let's figure out how much of this antibiotic is in the body after 6 hours has passed. So we're going to call this Q sub 2. So the first dose that this person took 6 hours ago, there's only 4% left, right? That's what this said up here. There's only 4% left after 6 hours. So there's 4% left of the first one. But then now they are taking another dose. So you have another 250 milligrams added. So if you do the arithmetic here, that means after 6 hours, you're going to have 260 milligrams. Okay, let's try one more dose. So let's say another 6 hours goes by, so a total of 12 hours. And let's see how much of this antibiotic is in the drug after 12 hours then. So same idea. So I'm going to kind of do it the same way that I did above. So the very first dose, this Q sub 1, now 4% is left after 6 hours, then another 4% of that after 12 hours. So really, this is how much is left of that first initial dose. Then the dose that was taken 6 hours ago, there's only 4% of that. And then now you've got the new dose being added again. So if you do this and punch this out, obviously you're going to have a little bit more. So you have 260.4 milligrams. Now, another way you could have done this is you could have just taken what was from Q2, which was 260, and we know we have 0.04 of that, and then add the new dose. And you get the exact same thing. But when you write it out this way, do you notice that this is a geometric series, right? What are you doing every single time? You are multiplying by 0.04. So that's your R value. Your first term is 250. That's what we start with. So this is a geometric series that does converge. So the sum is 250 A over 1 minus R, and you're going to get 260.42 milligrams. So this is saying in the long run, if this person is on this antibiotic forever, they're going to have this milligrams of this antibiotic in their system. So you can see how with drugs, they want to make sure they're not getting too much of the drug in the long term. Okay, last one, let's talk about a bouncing ball. So you've got a ball that's dropped from a height of 10 feet. So the vertical distance 10 feet, and then it's going to start to bounce. And it says the height of each bounce is always 2/3 of the previous height. So this is going to be 2/3 of 10. So it has to obviously bounce down, it goes up, and then, so this piece would also be 2/3 of 10. And I want the total vertical distance that this ball travels. Okay, so let's try to write out all the vertical distance. So this 10 only gets counted once. It just bounces from a height of 10 once. This next piece is going to be 2/3 of 10, but then it bounces up, bounces down. So I need 2 of them. The next piece is 2/3 of the previous one. So it would be 2/3 again squared of that original 10, and then you've got it again. Right? And this pattern continues. So notice you've really got a geometric series. So I can write this, the 10 only gets added once, so I'm going to write that once. But notice each term that's a geometric, this, you have 2 of them, this is 2 of them. So you're going to have 2 of the sums of the geometric series. So this is my geometric, but I have 2 of them. So A is going to be 2/3 times 10, that's my first term. And then R is 2/3, 1 minus 2/3. And if you do all of this arithmetic, you're going to get a total of 50. So that's the total vertical distance that this ball travels.